Hello everyone, I just wanted to work through an example with you that includes an old idea but looking at it through an energy lens, and that's this idea of friction. The situation that we're going to look at is a box sliding down an incline into a spring. Okay, so I'll draw the situation here. So if you think back to our forces unit, when we did this ramp problem with the box on the ramp and we had to look at friction, it was a fairly complicated problem when we were trying to solve it. But the motivation behind using energy is that it simplifies things just a little bit. So what's going to happen here is the box is going to start from rest. It's going to slide down this ramp. We're going to include friction this time. It's going to slide down the ramp and it's going to compress the spring. Whenever you guys are doing any sort of energy problem, you're always going to follow these steps right here. Remember, we wrote these out last time.
Test your might. Test your might. Test your might. Test your might.
First, we need to define what our system is. In order to think about what's in our system, we have to think about what are the outside forces that are acting on that system. And in this case, those outside forces are going to be friction. So everything else we need to include in the system. So that's going to be the box, the spring are all in the same system, and also the earth. So the system is the box, the spring, and the earth. Okay, our second step, we need to define our initial and final conditions. So I said that initially the box is starting at a height h, and it is starting from rest. So we can write down that V initial is equal to 0. Then we said the final situation, the box is going to be also completely still, so we have a V final of 0. But the spring is going to be compressed somewhat by this distance of x. So the box starts from rest, slides down this incline, and compresses the spring by a distance of x, and it causes the box to stop. All the while, the box is sliding down the ramp. There is some sort of force of friction. There's some sort of work done by friction that we're going to calculate. Okay? So, step 3, we're always going to conserve energy first and foremost, and then we have to draw our bar charts based on our initial and final conditions in our system. So, as always, we're going to set up our equation. So we have the total energy initial plus the work of the outside forces is equal to the total energy final. Okay? So we need to write down all of the energies that we know about in the system that could possibly exist in this situation. Well, we'll just start at the beginning. We know that there's gravitational potential energy initially. We know that there is some sort of kinetic energy initially. We know that there's some sort of elastic potential energy initially, or there could be at least, if we're looking at the most broad sense. And we're trying to apply this equation to any situation possible. Okay, and then we have plus the work done by outside forces, and that's going to be equal to, we have the same things over here except for that, so we have the final gravitational potential energy, we have the final kinetic energy, and we have the final elastic potential energy. Okay, so in every situation that you set up when you're doing energy problems, you have to write this equation, and then you have to expand it out to account for all the different energies that could exist. And we're going to come back to this equation in later units, so it's important that you know all of these different energies that could exist, because there will be more energies that we learn about. So now the next step is to draw our bar graph, our energy bar chart. So what we're going to do now, keeping in mind our initial and final conditions, we're going to systematically pick off each of these variables and think about, okay, should they be there or should they not be there? Okay? So gravitational potential energy, should that be there in the beginning? That is the question we need to ask ourselves. And in our situation, we said the box was up a ramp, up a certain distance height, so there should in fact be some gravitational potential energy. We'll give it 3. Alright, that one's done. We're moving on to this one. The initial kinetic energy. We said that our initial condition was that the box was sitting still. So that means that if something is not moving, it doesn't have any kinetic energy, so this value goes to 0. Okay, we did this one. Let's think about the elastic potential energy. Initially, when the box is up here, it's not affecting the spring at all. And therefore, the spring is totally relaxed and there's no potential energy stored in it. So this one also goes to 0. 0 here, we have 0 here. And now we have to think about the work done by the outside forces. We said the outside forces here were going to be something a little different. Remember, we said our system was the box, the spring, and the earth, but the one outside force that we didn't account for was friction as it slides down the ramp. The work done by the outside force on this system of the box, spring, and the earth, the work done on this system is the friction going down the ramp. And now we have to ask ourselves, is the friction going to be adding some sort of energy, like the rockets did on Charlie's skateboard? Or is it going to be taking away some of the energy? Well, it's going to be dissipating the energy from the system. So that means that our system is actually losing energy here. So instead of drawing a bar up to symbolize gaining some sort of energy from an outside force, we're actually going to draw it upside down because now we're losing energy from that outside force. Okay, so friction is going to be taking away energy from our system, from our box sliding down the incline. At the end of the day, it's going to slow it down just a little bit. And now we can look at our final situation. We said that the box was compressed, and it's all the way at the bottom, and the box is also not moving when it's compressed the spring entirely. So if we're at the very bottom, there's not going to be any gravitational potential energy. If we're at the bottom and the box isn't moving, there can't be any kinetic energy either. And if the spring is compressed, it means that there's going to be some sort of energy stored in it, and that's going to happen to be the difference between this bar and this bar. Initially we had 3 units of total energy, and on the journey down we lost 2 units. So at the end of the day, we're just going to get 1 little unit of elastic potential energy at the end. Step 4. We need to set up our equation and solve for what it is that we're trying to find. So let's set up our equation now. So we have the gravitational potential energy. Remember, that equation goes like mgh, initial, the mass times gravity times the height. This one is 0, this one is 0, and now we have this work done by friction. But notice that instead of adding to the system, it's going to be taking away. So we actually have to subtract the work done by friction. And what we have to do, what is the equation for work? Well, that's force times distance. So we're subtracting this force of friction. Don't confuse friction and final. This is the force of friction and the distance that it travels down the ramp. So we're going to have to define a new variable in our system here of distance down the ramp, which is just the length that it travels. That's what that d is right there. And then we can set that equal to our elastic potential energy equation, which is 1/2 kx squared. And now let's say, I don't know, you choose. What do we want to solve for? Let's say we're trying to find the force of friction. That acts on our system as the box slides down the ramp. So if we solve this equation for friction, we have to do a little algebra here. And there you have it. There's an equation for the force of friction. Now, if we look at this equation, we should check back and think, okay, does this make intuitive sense? Well, I think it does, because we have the force of friction. It's going to be the difference between this initial energy that we had at the beginning and the final energy that we had at the end. This is going to represent, the difference between these two represents all of the energy that the friction sucked up. So, just to review, always, we're going to follow these 1, 2, 3, 4 steps as we go through these conservation of energy equations. Okay? Today we looked at friction and how it applied to something sliding down a ramp. Step 1, we defined our system as the box, the spring, and the earth, and we defined our initial and final conditions. We set up the conservation of energy equation, which we need to do every single time we do a problem like this. And then we thought about our bar charts. The key thing to remember here is that friction is taking away energy from the system as the box slides down the incline. And therefore, our bar chart needs to be in the negative direction. And then when we set up our equation here, we of course subtracted the force of friction times distance. Remember, force times distance is the equation for work. And then we can solve for various things, whatever